1000 Newton. A is the area above the level of neutral axis, because our intention is to find out the shear stress at the neutral axis. So the area A, that is the hatched area above the level of neutral axis, if you want to visualize on this tabletop, this is by area A, and we know 100, that is the base width, we know 300 is the height, so we can find out easily area A is equal to half into 100 into 300, that is 15,000 mm square. Y bar, that is the distance of the CG of the area A from the neutral axis. If you want to refer this figure clearly on the tabletop, this is the CG over here, and this is my Y bar, and this is nothing but Y bar is equal to 1/3 into 300, that is 100 mm, clearly shown over here, where I is the moment of inertia of the total section about neutral axis, moment of inertia of the total section about the neutral axis. Now if you want to refer a figure over here, the given section which is of triangular, this is of 450, this is of 150. I want to find out this moment of inertia about neutral axis, and moment of inertia about neutral axis is 1/36 bh cube. And if you want to find out base, because this is my base, I base is equal to 1/12 bh cube. But we have to find out about neutral axis, because we have to find out the shear stress tau at neutral axis. So we have to find out the moment of inertia at this level with the formula 1/36 bh cube. So that is the base width into height cube by 36, that is 1/36 into 150 into 450 cube mm raised to 4. So B, that is the actual width of the section at which the shear stress is to be obtained. Here the shear stress to be obtained at the neutral axis, and we found out the base width at the neutral axis is of 100 mm. Hence, placing these values in the equation, the shear stress tau is equal to Fa y bar by Ib. We know the F 30,000. We know the area 15,000. We know the value of y bar. Y bar is the distance of the hatched portion to the neutral axis, that is 100 mm. We know the value of I, 1/36 bh cube. We know the value of B. By simplifying all these things, use your calculator, and we found out 1.185 Newton per mm square megapascal is the answer of the shear stress at the level of neutral axis. So from problem number 1 and problem number 2, for the first part, you can easily visualize how to find out the value of shear stress at a one particular section. Let us go for its second part. What is the second part is going to ask? Second, the intention in the second part is to find out the distance from the top of the beam where the shear stress is maximum. Please refer what the things which has been asked. The distance from the top of the beam where shear stress is maximum. Let us understood this concept over here on this tabletop. What the question number 2 is going to ask. Now this is a triangular section which has been given to us with the height of 450, base width of 150. Our intention is to find out a one specific section, this one or this section from the top to obtain tau max. I want to find the tau max. We do not know the just location. So our intention is to find out the specific location where we got the tau max. How to achieve? Think and let us proceed further with the solution of this particular problem. So now refer the PPT. Let the shear stress is maximum at a section EF at a distance x from the top. Refer the figure. This is the section distance x from the top. This is the layer EF, where we are assuming that this is the layer where the stress is maximum. We are assuming distance x. So the distance EF is obtained from, because I want to value find out EF. This EF we have to find out to obtain the value of B. This EF which has been found out to obtain all the related parameters. This EF is obtained from the similar triangles of BEF and BCD. Now let us proceed further. So EF by CD is equal to x by 450. This EF by CD is equal to x divided by 450. So we achieve x by 450 into CD, that is 150. We achieve is equal to x by 3. That is the value of EF. So we achieve the value EF is equal to x by 3. Now the shear stress at any section EF is given by tau is equal to FA y bar by IB, where F is equal to 30,000 Newton. A is the area of the section above the level of EF, that is the area of shaded triangle BEF. We want to refer the figure. I want to find out the area of this small triangle BEF. Why this triangle? Because we have assumed that the distance x value, the maximum shear stress is acting at this layer. So area we have to find out of this triangle, and that is equal to half into EF into x. And we know the EF, that is x by 3 into x by 2, that is area we achieve x square by 6. Y bar is the distance of CG of area A from neutral axis. Refer the figure. This is the area A. Here area A. Distance from this CG, this is the CG, to this distance is y bar. We know that this distance is, what is the value of that? We know that value, that is x by 3. So this value is 2x by 3. So we can find out it is as 2h by 3 minus 2x by 3. If you want to refer the figure clearly, 2x by 3, it is the total distance available, this one, minus 2x by 3, we obtain the value y bar. So h is known to you, that is 450. So 2 into 450 by 3 minus 2x by 3. If you are simplifying this, we achieve y bar is equal to the bracket 300 minus 2x by 3. So you just visualize all the terms, area A, y bar, all the terms are comes in the correspondence with the value of x. So I is nothing but the moment of inertia of ABCD, moment of inertia of ABCD section above the neutral axis. That is interesting point, above the neutral axis, 1 by 12 BH cube. Moment of inertia of ABCD about neutral axis, about the base right now. So 1 by 12 BH cube, that is for that one. So Base width of the section is x by 3. We are putting all the values over here. F is equal to 30,000, A is equal to x square by 6, y bar is the 300 minus 2x by 3, B is equal to x by 3. And if we are simplifying this, we achieve an equation. Shear stress is equal to tau is equal to 0.40395 bracket 300x minus 2x square by 3. So, for maximum shear stress, d tau by dx is equal to 0. And we do perform that one, we achieve 300 minus 2 by 3 into 2x is equal to 0. So we achieve x is equal to 225 mm, 225 mm. Hence the shear stress is maximum at a distance of 225 mm from the top of the beam. It means that at that particular layer we are achieving the maximum shear stress. Now, our intention is to find out the maximum shear stress. We found out the value of x. We found out the level at which the shear stress is maximum. So, the value of maximum shear stress will be obtained by substituting the value of x as is equal to 225 mm in this equation. So, maximum shear stress tau is equal to 0.40395 bracket 300x minus 2x cubed by 3, and we are placing the value x is equal to 225 mm. We achieve it is as 1.333 megapascal. So with this solution of the two problems, our next session, let us we found out the shear stress distribution for different section, specifically rectangular section, circular section, T section, and other unknown section. So in the next session, in the next lecture, we are discussing this part. So what we today learn? We today learn the derivation of the shear stress equation, and the answer is tau is equal to Fa y bar by Ib, and we have solved certain numericals. I wish you have obtained the fundamentals. I wish you will solve certain more numericals at the rooms, and I wish in the next section you will proceed further with these equations. Thank you.